right, so again, the purpose, the idea is we're blowing on the soup or the hot chocolate with warmer breath than the classroom. Does that really cool it off faster, or is it just giving us something to do? Akrit, give me a number.
1.
1. All right, David, what'd you guys come up with?
I don't think we really got the correct idea, but we talked a little bit about perhaps convection, like would cause, when you're blowing on the soup, would cause colder air to come down because your warmer air starts to rise after. But I don't think that's correct. I don't know.
All right. All right. Other thoughts? Anybody else want to share? David, give me a number just in case.
6.
Anybody else? All right, Zaid, what'd you guys come up with?
Yeah, actually, Akir was raising his hand, but okay.
Oh, I didn't see.
I was in his group.
Sorry.
I was gonna say just basically what Akir told me in the group. He said that it would be faster because you're blowing the air at a, like, even though the temperature is higher, the rate at which the convection occurs is faster because the air is moving faster. And he said like something about that causes the temperature in the soup to decrease, or in the hot chocolate. That's what he was saying.
Okay. All right. All right. So convection works better than conduction. All right. I think we nailed that idea down. Did anybody come up with a reason for why that's the case? Why does convection work better than conduction? The flow, why is that better? All right. I did. I'll share with you. Let's see. Here we go. So here we go. Why does conduction actually work? Why does heat transfer? Remember, heat transfer happens because of a gradient in temperature, a difference in temperature, right? So if your hot soup is at whatever temperature it's at, let's say it's at 50 degrees Celsius, okay? And then the air is at, 25 degrees Celsius, okay? Then what happens is, remember, the particles at the surface here are bumping into each other, right? And so the average temperature of the particles at the surface of the air here, they're going to start changing, right? Some of the particles at the surface are going to take some heat away from the soup at the surface of the soup. And some of that will get transferred down into the soup as those particles collide, right? But what's going to end up happening is that here at the surface, it's going to come into an equilibrium, right? Where the particles on the surface of the soup are at almost the same temperature as the particles in the air right above the soup, right? Because nothing's moving, it's just the particles bouncing into each other, right? This air essentially is acting like one of those carbon pipes or the glass that we were talking about in the window, right? There's going to be a gradient in temperature. And as we get farther away, it's going to get cooler and cooler. All right, same thing in the soup. At some temperature, it's going to go down. You probably noticed this when you had your hot cocoa or your soup, that sometimes you could start scooping it off the top, right? Because the top had come to some type of equilibrium with the air. And so you can eat off the top first because it was actually cooler, because that's come to a cooler temperature. Now that's great. It means that you can eat the top or drink the top of whatever it is. The problem there, of course, is that if there is no more gradient of temperature because it's come to a balance, then your thermal heat transfer slows down. It becomes significantly slower. How is this different when you blow across the top? Even though it's 50 degrees C and possibly 37 degrees C with you blowing on it? Well, the particles at the top aren't going to come into an equilibrium with the 50 degrees C, right? Because these particles are going to get pushed out of the way by new air, which is 37 degrees C, which means that the air here will always be 37 degrees C. As long as I'm blowing on it, the air right above my hot liquid will always be 37 degrees C, which means I'm always going to have a large temperature gradient. Whereas in this side, the temperature gradient got really small because it came to kind of that balance. In the idea where we have convection, because of the moving fluid, these particles are always being replaced with particles that have a lower energy, which means there's a greater temperature gradient and therefore heat will transfer faster. Does that make sense? Questions about that? It's all about the temperature gradient. As long as you can keep moving those particles out of the way and keep that temperature gradient there, you're going to have higher heat transfer. And somebody said this, I think it was maybe Akrit, said that it's very, very similar to conduction. It's still contact. You still have to have transfer, but the difference is that you're going to constantly be having a large gradient. We're not going to do any calculations with this one. AP doesn't require it, but there is another equation that gives you a heat transfer or conduction, a thermal conduction coefficient for convection at specific speeds. And so there's a different thing there, but you don't have to worry about that in this class. If you go into some type of engineering, you'll probably look at heat transfer and look at that in more depth. In fact, I had a whole class on heat transfer. So yeah, you'll look at things like that. Okay. Any other questions? All right. What are some examples? What are some examples of convection where the movement of fluid causes something to be cooler, or as Akrit was mentioning, the heating of something causes a change in density, which causes air to flow, or some other fluid? What are some examples of convection?
What about like a tornado?
Okay, tell us about a tornado, Akrit. What happens there?
Well, I don't know. I've never seen a tornado, but I can like it's kind of like I don't know, and I'm probably wrong here, but it's kind of like mirage where the ground is warmer than the sky, and in mirage's case that bends the light, but in the case of tornado, it causes there to be a temperature gradient between the um, ground and the sky, and so obviously there has to be some like initiating factor, like a I don't know, like a hurricane or something, but then the convection is what keeps the tornado going. You know, I don't know. This is just This is probably wrong.
It's a good concept of the idea that somewhere there's created an area of low pressure. The high pressure goes to the low pressure, meaning that the air starts moving and causes a transfer of heat and energy. Obviously, there's a lot of energy inside of that tornado. So yeah, that's a good example of a tornado starting is due to convection. All right. Boiling, simple boiling is convection. What happens when you boil water?
The parts of the water rises to the top, and then eventually they'll cool off and fall back down the side of the pot again.
Yeah, so at the bottom where you're heating it up, that water turns into gas, which then is a bubble, and that bubble rises up through your fluid, right? As it rises through the fluid, it's that motion of the air, the water vapor going through the liquid water. And if you should watch, if you haven't ever seen it, watch a slow-mo video of boiling. It's really, really cool because you see these bubbles, and as they rise, the bubbles get smaller. The bubbles get smaller as they rise to the surface. And the reason is because of the convection between the water vapor and the liquid water, heat is transferred to the water and actually causes the water to heat up faster. Much faster than if the water was just still. And so you get the bubbles to flow, and it does actually heat up the water faster. And then, so then you're right, and it gets to the top, and then the movement then causes more water to go down to the bottom. When the water goes down to the bottom, it heats up more, and the whole thing heats up faster because of this motion. All right. Okay. I think that's good. The other one that we should mention is like a sea breeze or a land breeze. If you've ever been on the coast, you may have felt in the morning, the wind blows one way, and in the evening, the wind blows the other way. That has to do with the different temperatures of the land and the ocean. Okay. One of them heats up faster. Land warms up and cools off faster than water does. So in the morning, when the sun comes up, the land warms up, the air changes density because it's over the land, the air goes up, and so the breeze comes in from the sea. That's convection. It cools things off because of the difference in density, the difference in the temperatures over the land and the water. At night, the opposite happens. The land cools off faster, so the air becomes more dense, meaning that it goes from the high pressure over the land to the low pressure over the water. And so you then get what we call a land breeze going out to the ocean. All right, why don't we take a quick break? I know it's been almost an hour, so take a few minutes, get up, move around, and when we come back, we'll talk radiation and hopefully start on thermodynamics. All right? What did you discuss? What were some of the ideas that you had?
Well, we just kind of talked a little bit about homeostasis, but we weren't able to come up with like anything else.
Okay, so I think that's a good idea. You know, those that have been through biology, or I guess you've all been through at least a basic biology class, there are some objects that create their own energy, right? Like our bodies can create it from chemical and potential energy. Right? So some objects can do that, especially if the object is warmer than everything else around them. Right? So that's a good point, is that yes, some objects maintain their temperature by creating their own energy. Of course, to do that, you have to fuel it. Therefore, you must eat. And so you constantly add energy in through the food that you eat. And so it's a conservation of energy. Yes, you keep radiating energy out, but that's why you lose energy even if you lay down all day, right? You burn calories just by laying down. Part of it is, you know, your brain working and doing things, but it's also because your body is constantly radiating energy. It's losing, right? Okay, awesome. What else? Anybody else? Tarek, what'd you guys come up with?
I was with Krisha.
Oh, awesome. That's lovely. Ram, what'd you guys do?
So I mean, basically Isaac, he was talking about how even though we are constantly losing energy, we receive energy from other objects radiating energy. And so one example that I was just thinking about in my mind as I was connecting back was sun. Maybe the sun radiates energy, and that is a potential source of energy, I think, for all human beings. So that's how, even though we are losing energy through the sun's radiation of energy, we receive energy.
Okay, awesome. Yeah, there has to be some kind of energy balance, right? You can't just focus on the energy going out. There's got to be energy coming in, right? We were talking about the metal pole and the wooden pole last class, right? And how they were at some type of thermodynamic equilibrium with the air around it. Well, that's because the wooden pole, the metal pole, the tree, the leaves, the ground, the grass, everything outside is at the same temperature. Now, if everything outside is at the same temperature, then it's all radiating energy, which means not only is the metal pole losing energy at a certain rate, it's also gaining energy from everything else around it, right? The wooden pole is radiating energy towards the metal pole. The grass is radiating energy towards the metal pole. Everything is getting energy from somewhere else. And certainly the sun is part of that, right? The earth is losing energy to the rest of outer space. So it's got to be getting energy from places as well. And a lot of that is coming in from the sun. So good, there has to be some type of balance. And that's how objects, even inanimate objects that can't maintain their own temperature, will, because there's always energy coming in from all of the other objects around it. An object that has a larger surface area that loses more energy also has a larger surface area so that it can gain more energy, radiation from everything around it. So good, those are good ideas. And I think that's really what we wanted to hit on with radiation, just recognizing that everything is letting off radiation, which is a light wave. Okay, I believe you guys covered waves last year in Physics 1. So it's a light wave, which is being sent off. It's a very low frequency or long wavelength, so that it's something that is not very energetic, at least in the case of us. But Ram, you pointed out the sun, which is sending very high energy waves over, which is why you stand outside and you get a sunburn, whereas I can stand in front of my table and never get a table burn from the radiation coming off of that. So it's a difference in temperature, energy, right? All of those things come together. All right. Any questions before we? Okay, I'm not seeing any hands, so we're gonna. Awesome. All right, so I got what, 15 minutes left? It's not enough. It's not enough. It's never enough. That's all right. We'll start on it. Okay, so what we've done up to this point is thermal energy. Okay, it hasn't really technically been thermodynamics yet. We did do the zeroth law of thermodynamics. Remember, is that two objects in contact will come to a thermal equilibrium. So we did do that, but otherwise we haven't really been doing what we generally consider to be thermodynamics. We've just been studying thermal energy and how does it transfer and things like that. All of that was leading up to this so that we can now start looking in depth at this idea of what we call thermodynamics. And we really are just going to brush the surface. Again, if you do anything more with chemistry or physics or engineering, you're going to take a whole course or multiple courses on thermodynamics and really dig into this and the details and things. We're really just trying to give you a flavor of it, a little taste of what thermodynamics is. All right. Now, thermodynamics is really trying to connect, and I mentioned once, just kind of in passing, the conservation of energy. Right, where we have the internal energy, the total energy of an object, which depends on the work, which you've done before, but now we're adding heat into that equation. We're saying that now I can do work on a system. I can add heat in through these thermal processes of conduction, convection, and radiation. We were talking about ideal gases, where we could do work on an ideal gas and cause the pressure to change, or the temperature, right? The temperature was the internal proportional to the internal energy. So all of these ideas connecting work and energy and things like that, that's really what thermodynamics is all about. And so we're going to really start on that today. All right. Let's look at we're gonna skip partner chat number 10 in the notes. We can chat about, we'll talk about it kind of as we go. One thing to mention is, thermodynamics, we use it when we talk about engines, whether it be car engines or motorcycle or jet engines, which is a completely different type of engine, but engines use thermodynamics. Your body uses thermodynamics when it's creating the energy. You guys all talked about homeostasis, so creating the energy that is needed to maintain a body temperature. So that's thermodynamics. An air conditioning unit or your refrigerator, that's thermodynamics. How do we take the energy from the wall, plug something in, and yet get it to cause a change in the heat or the change in temperature? That's all thermodynamics. And so that's really what we're going to be looking at here over the next couple of days and trying to put those ideas together. So the first law of thermodynamics is this. First law of thermodynamics is looking at the internal energy of an object, which is usually noted by delta U. And it says that the change in internal energy is equal to the work plus the heat. All right, and that's it. That's the first law. Now, in AP, this is a convention. Okay, you've probably talked about different conventions before when you did rotational dynamics. Counterclockwise is positive, clockwise is negative. You can work it the other way. You can make counterclockwise negative and clockwise positive. It doesn't matter as long as you're consistent. You've done conventions when you did objects on a ramp, and you took your X and Y axis and tilted it, and you changed the convention. You said, I'm going to use this as my X axis and this is my Y axis, right? And so those are conventions. So the convention we use in AP for the first law of thermodynamics is that we count positive energy. We count work as positive when work is being done on the system. Work is being done on the system, which should add energy in. We count Q as positive when heat is being transferred into our system. Okay, so work and heat are both positive when energy is coming into the system. Work is being done on the system, heat is being transferred into the system. Both of those obviously are going to cause an increase in internal energy. We talked about work, right? When you push down on a piston and it causes all the molecules inside to start moving faster because you transferred energy to the molecules, you just gave them a whole bunch of energy, that increases the internal energy. We've talked about heat. You take something and you heat it up, you put a fire under it, it increases the internal energy. The molecules start moving around faster because they got more energy now, right? So that should make sense. Now, I mentioned the idea of a convention because this is how we do it in AP Physics. I noticed that IB does the same thing. However, there are many college university courses and many university level textbooks that use work the opposite way. They say that work is positive when the system is doing work. And so it changes your equation. The concept is still the same, and I want to mention it, but I'm not going to say anything more about it. I just don't want you to get to your university level class and say, Mr. Bauer lied to me. He told me that work is positive when work is being done on the system. No, I'm not lying. I'm just giving you the convention that we use in AP Physics, and I'm being straight up that you're going to come across situations where that convention is different. All right. So, questions about the first law of thermodynamics, which we're going to look at over the next couple of days. All right. It's worth mentioning because we use his unit, we named the energy units after Sir James Joule. It's really worth mentioning because he did this experiment in the 1840s, 1850s, and the accuracy that he used, I read somewhere that James Joule's biography is likely one of the most significant biographies of a scientist ever written. And of course, that's somebody's opinion, but the work that he did with thermodynamics was absolutely amazing. What's that?
Nice one there. The work he did with thermodynamics.
Yeah. I'm good at those puns. So the work that he did there is very amazing. And one of the things that he did is the experiment that's shown here on this page. And what he did was he put a mass on the end of a string. And so as gravity did work on the mass, gravity pulled the mass down, it was then wrapped around that wooden thing at the top here. So the string goes up here, it wraps around this. So as the mass goes down, it causes this to spin, which then causes the paddle wheel to spin, which very literally pushes the particles, right? And gives them some extra kinetic energy. Now, what he measured, he kept this isolated from the outside. He used insulation, and he would do this, raise it, and then drop it multiple times. And he was able to very accurately show that the amount of energy gained by the water, as in its temperature, its internal energy, was proportional to the amount of work done by gravity pulling that mass down. And if you can think of when we do labs and how difficult it is to be accurate, even with simple things like trying to measure the speed of something dropping, something like this and being so meticulous and accurate was just amazing, especially at any time, but even, especially at his time. And he was able to, he created, a discourse, basically, his most famous one, which equated work to internal energy and said that there is a relationship here. And he was the first one that really was able to connect all of the thermodynamic ideas, not just that heat can cause a temperature change, but work and heat were related to each other. And so I feel like that's an important thing to mention as we move forward. What I would like for us to do just to finish off here is example number 12 here. Okay, in one of Joule's experiments, the one up above, an object of mass 12 kilograms descends a distance of 1.25 meters at a constant speed, causing the rotation of the paddle in the insulated container. If the descent is repeated 20 times, what is the heat transfer to the water in joules? All right. So, can we find out how much work is being done?
Yes.
Okay, how so?
Because you have the weight, the mass, and since you can find the force down because of that.
Okay,
and
so,
also have
yep.
the distance, so you can find work.
Good. So we know that the force is the force of gravity pulling the mass down, which will be the mass times acceleration of gravity, which is negative 10 meters per second squared. It's close enough. And then multiply by the distance, 1.25. And we'll get the amount of work for one drop. What you got?
$146. 47, sorry.
9.8.
Yes.
That's fine. If you use 9.8, you'll get 147. If you use 10, I think you get 150. So either one is fine. So that's for one drop. If we do it 20 times, we get about 3,000 joules. And that's the total heat transfer. That's how much work was done. That's how much heat or energy the water will gain. Now, to put this in perspective, that's not even enough to raise a liter of water 1 degree Celsius. So this gives you an idea of how difficult and how meticulous Joule would have had to have been, right? And that's a decent sized mass, a 12 kilogram mass, dropping, you know, the height of your table 20 times and doing that quickly enough so that heat isn't being lost to the outside, right? So obviously we're making connections, work, energy, all these other things, but we're also recognizing, you know, how amazing these things were that these guys were doing. Okay. We're going to stop with that. I think this is a good stopping point, that and the fact that it's 10 o'clock. So we'll go ahead and end with that. And that's it. So,